right. So thank you all for coming. Hopefully whoever after this watches it, they might be able to take away some of the things that I've learned over the past 2.5 years and digging into subtractive manufacturing, like CNC processes and in general design for manufacturing, design for assembly type stuff. And we'll go ahead and switch over to a little PowerPoint. So let me know when y'all can see my screen. You see my screen?
Yep.
Yep.
All right, cool. So let me hide some of this stuff real quick. And if y'all have any questions, like interject or whatever, do your thing. Let's see. Go to slideshow. All right, so I wanted to go over basically CNC practices and what CAM is, and then kind of what you can take away from it, and then at least design kind of for it, depending on what your capabilities are. I'm Dan, one of the Dans, and I will be your instructor. No. So basically, I'm graduated mechanical engineer. For anybody that sees this, it's not on the team that doesn't already know, and from the University of Florida. I love subtractive manufacturing, all of the CNC stuff. I'm huge into 3D printing stuff, but my life is with these guys. And then I'm also a high school robotics mentor, which is some of the people here, and then a Navy veteran. So moving on to what exactly CNC is for the people that don't know. It's a computer numeric control. A lot of different processes or machines follow computer numeric control. It's just sending it some sort of data or whatever, and it follows that path. And you can pre-program that and run it over and over and over again, which makes it pretty fantastic. So it really helps us to iterate through our designs. And then, you know, if we get to the point where we're doing some accurate, but also we're still kind of rapid prototyping, we can cut it out of wood or plastic before we go to aluminum. It's really good for 3D cuts. Like, good luck getting some of those 2D contours with a manual mill. You can approximate it sometimes with hand tools and whatnot, but for the most part, it's pretty impressive with the different curvatures you can do. And then even 3D tight pockets, 2.5D 3D pockets to get around whatever you need to. So it's pretty amazing. And then the process can actually be optimized going through some of the paths included in Fusion 360 and some of the other stuff that I'm going to mention later. It's actually smart enough to go through and realize, hey, this might be more effective and I can move to a different spot, let that side cool down a little bit, come back and do this other process. You'll have better results because you don't have so much heat buildup, and you'll have more reproducible, accurate, and an overall better product if you use some of these. However, some of them can be time consuming, and you kind of have to make that trade-off between the two. And the biggest part of CNC for me is being able to just run a ton of these things. So we're able to reproduce parts, and as long as everything doesn't like shift or it doesn't have an issue where the end mill breaks or whatever, you can just go and go and go. And that's the best part, especially for parts that we use all the time, like gussets and whatnot. If you have to do a bunch of them, ideally it might be in a water jet, like a giant sheet. You can use an abrasive water jet, which we'll go into later, and cut out all those. But if you're on a CNC, you can nest all of those things together, organize them like Tetris, and then cut them out. It's going to get here faster than a lot of the manufacturers that we typically buy from. So one of the main reasons that I really dug into it in the first place was for the team to move through designs and get, let's say, 90 thou gussets from AndyMark or wherever. You could get 3, 5 at a time. Shipping is $1 zillion, and it takes a while, a couple weeks sometimes in build season, and we just don't have that type of time. So if we need something that's a specific degree, then that's even a bonus on top of it because we can custom make it. But if we're doing like 90s and whatnot, we can have those almost immediately. And then on top of that, we might be able to pick an alloy of the aluminum or whatever we want, typically aluminum, to reflect our design, whereas we're kind of at the mercy of whatever they have in stock or whatever they run. So it really opens up the possibilities of your design process. And we've kind of taken that forth into a mix between commercial off-the-shelf stuff and a custom angles and whatnot to go onto our chassis. And I think it's worked out really well with the combination of the two. So you can move into a portion where it's straight custom. You do everything, 2x1, all that stuff. Probably not where we are right now, but it definitely is there. So moving on to, why is this a thing? So design for manufacturing, and why I'm trying to bring this up right now is moving into the next build season, further, all that stuff. You have to think about, okay, what actually do I have on hand? What machines, what tools, if I make something that is some amorphous blob that fits into the design, but you don't have a 4, 5, 6, 12, whatever axis CNC, you don't have a 3D printer, you're not making it. So you have to think about that when you get into the design process, and you can actually make things all the time. It's not hard to make things that just can't be manufactured. Even with some of the most incredible machines out there, it's just not a thing. So keeping that in mind whenever you're designing all of your parts, how they fit together, fasteners, all of those things, and then actually putting it together. So design for assembly, can I actually take off the bolts whenever I'm in the pits? Can I get to this part after I put it all together? Am I actually going to be able to assemble this thing? You can make holes on one side that you just can't get a screw to, and then affectionately call it DFTS, BMIT, WTPW, blah, 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 blah. So design for 30 seconds between matches in the pit while we're changing bumpers and everything is broke because we yeeted onto the hab. That happened. So we had a pretty awesome experience, everybody, yay. But camber gang, sitting like this, everything was broken pretty much, and we were trying to get to the parts, and we actually had to take off a good portion of the robots so that we could get to the tensioners to retension everything, get back out there and break it again. You got to think about those things whenever you're designing. And then that type of thing, you need to keep in mind what tools do you have on hand. So if you don't have a CNC or you don't have a water jet, you don't have any of this stuff, then you have to come up with some other ways to go about what you need to, or simplify your design to the point where if you need to make it, you have to buy COTS from AndyMark or wherever, then that is what it is. But if you do get something like a machine behind me, you can make your own parts, you can do your cuts, and you can continue moving forth with, for instance, a piece that we would be able to cut out pretty easy on a CNC or a water jet or something like that. But if you wanted to do this by hand, it would be miserable. Like, I don't even know if you could do it because of all the fillets and contours, holes, different sizes. You could probably locate all these guys, but it takes so long. And this took, I don't know, 4 or 5 minutes on the CNC. And then in the design process, I had spec'd it out for one type of cutter, and I don't have to change that. So it's one setup, run it, and you're done. And now you have a piece that can hold a bunch of electronics, whatever you need to, and it's there. So that's the sort of thing that you have to keep in mind, and the thing that you have to think about moving forward. And then that's what I'm saying. So know your capabilities, know what you have on hand, what you can actually design. Can you design something that can be manufactured using these guys, or do we have to do something by hand, or do you have to outsource it? That's also a viable option, to design things so that other people manufacture it. They send it to you. It's pretty much everything where it's supposed to be. You have to wait, and it costs, but for the most part, it's exactly the way that you wanted it. You can also design so that they can't assemble it, or I'm sorry, they can't manufacture it. So taking all that into account is probably one of the more important things I wanted to keep in mind. So on the CNC front, I'm going to go ahead and switch gears to that because that's the main focus of this. And then I'll move into the CAM portion, but always safety with these guys. The tool can move around rapidly, like 100, 200 inches per minute. And that's very fast. And if you're trying to move your hand around or something around the cutter's spinning at about 24,000 RPM sometimes. It's cutting aluminum, so it will have no problem cutting through you. So keep in mind all of that stuff because it's really, really dangerous. And you should be definitely wearing proper PPE whenever you're around these guys and they're spinning specifically. Safety glasses always, and then you don't want anything to grab into there. So you don't want anything like hanging, no loose stuff or whatever. You want to make sure you're wearing pants and closed-toed shoes because chips are hot. That's kind of the point of evacuating them in big chunks, is to evacuate all that heat and not leave it in the workpiece. So when it evacuates that, not only is it throwing it at you at about whatever, it's spinning at 24,000 RPM and is launching those chips at you. They can be very hot and they can also be dangerous to your eyes and everything. So that's number one. And then, of course, hearing protection. Aluminum is very loud. The air system that they use, and you would probably use maybe for cooling down the chips or blowing away the chips so that you don't continue eating through them, is loud. And then also the vacuum, if you're using some kind of suction on there, that's also very loud. So the combination of all of those things can damage your hearing over time. It might not even take that long. So always take precautions when you go through, and then make sure that you have the shields up or whatever type of enclosure. If sometimes there's no enclosures, if you happen to have a machine and you want to make an enclosure or whatever, I mean, CNCs are awesome for that type of stuff. So you might be able to get creative and come up with your own thing, but it wouldn't take much. And it also minimizes the amount of cleanup because those chips, when they launch, they can go very, very far. So make sure that you have everything you're supposed to wear, you're paying attention to what's going on, and you have everything protecting the environment and you from the chips as much as possible. You shouldn't be reaching your hand through there anyway when anything's happening. So there's no need to get to that point. And if an end mill goes, it goes. You're not going to save it. You can e-stop everything, but again. So here I am setting a bad example. No, I've got my hearing protection, which is great. I actually have a watch on, which is not great. So that actually came off later, but I was wearing it to show everybody what not to do. And then wearing shorts, not great. That day was, I was not thinking. And I made sure and carried that forth into the further examples. But you can, let's say that you kneel down, so you're like cleaning or whatever, then the chips can get onto your knees and scratch you and get embedded. And that's always kind of a pain. We also want to wear safety glasses whenever we're cutting. So that would be kind of on the table. And then definitely have closed-toed shoes, which, yeah, it's kind of miserable getting those hot chips down near your toes and stuff. So the types of end mills that we can talk about, shifting gears a little bit, for the different materials is it varies a lot. And they're essentially split into a few categories. One is considered an upcut, the other one's a downcut, and it's not just an upcut downwards, so this is wrong. The second one is what you'd be looking at. And then a compression actually has a combination of two. And there's a really good video that I have in the PowerPoint later that goes into detail as to what it looks like whenever it's moving through the material. But for an upcut, they have chip evacuation is number one. You want to get that heat out if possible if you're building up a bunch of heat. And with a metals is what we normally cut for robotics, then you're going to want to take those chips and just throw them out of the way. And with the upcut, I'm hoping that I can maybe show it. Can y'all see the end mill? Hello?
Yeah.
Okay, cool. All right, so as the end mill moves through the material and it rotates clockwise, the chips are going up through the flutes and then they can get tossed out. And you can kind of see on the upcut, if this was rotating clockwise, then that is going to be carving into the material and it's going to be pulling it this way. It's also going to be pulling the material upwards because for the same reason. That's kind of how it works. So the other side to that, if you're running materials that are like plastics or wood, I prefer it in wood, you would have a down cut. So when it moves through, it pushes those chips downwards, but it also maintains the surface on top and it doesn't tear out in the way. And this is a little bit kind of smaller, but as it moves through in a clockwise fashion, the chips don't come up and out. The chips don't come up and out. They follow the flutes down into the material, the substrate. So it's very important to kind of figure out what, number one, what material you're cutting. Two, what your end goal is. Do you care about the surface finish on top? Do you care about going as fast as you can to get rid of the stuff? And anything in between. So a compression bit is a combination of the two. It actually has upcut on the bottom. So it'll rotate through and the chips will come up this way. And then it has a downcut up top. And that maintains the surface on the top of the workpiece because it's, you plunge down enough that it's pushing down into it, but the upcut pulls up. So if you go all the way through the material and the bottom of the end mill is sitting at the bottom of the of your workpiece, then it doesn't push that down through the bottom and create the same issue that you would have as if you were pulling up from the top. And it's actually a pretty interesting end mill, but we really can't use it that much. It's more for wood and things that don't act like metals and plastics where they get melty, stuck in the flute, and then they're done. They snap, they dull, all that stuff. So you typically don't run that, but if you do, you go essentially full depth of cut with it all the way down into the material and just move through it at some rate and it'll cut through everything. And I've done 80 to 100 inches per minute, full depth of cut at like half inch depth of cut, full material. And at I think 17,000 or 18,000 RPM, which is different from, for instance, an upcut on aluminum. We'd be looking at anywhere between 30 to 60 thousandths of an inch at 36 to 40 inches per minute at around the same RPM, like 19,000-ish RPM. So you're talking many, many multiples of what you would be cutting in the same sort of fashion, but it's the different materials and how they react when you go through. So picking the right end mill is critical for your success. And for metals, aluminum, we don't normally do steel, but you can also do steel. I'm just going to refer to aluminum. For flutes, as you move through, you have a flat bottom. So if you were to move down into some pocket and clear that material, it would be flat at the bottom, which is great. And it has more flutes, so it ends up having a better surface finish in almost every direction, either axially, which is with the axially would be pushing down on the material, or radially, which would be perpendicular to the cutter. So as you move through, you'll have more dependable precision and accuracy with more flutes as long as you're following the guidelines from the manufacturer and your machine can help it. 2 flutes is a really good balance between what we normally would experience. There's a ton of materials that it's one of their favorite combinations so that you can get that flat bottom up top. You're not going to get as good of a surface finish, but you're going to be able to evacuate chips better as it moves through. And that's going to be really important in metals because chip evacuation is where it's at. And then my love of my life is O flutes. They have a single flute that has a huge opening. The backside, some of them have facets, other ones don't, but this one doesn't have that flat bottom. So if you're doing facing passes, which is just going over a workpiece and trying to make sure that the top part is flattened, once you step over, which is going over to your next part, so if it goes this way, the next step, how much it moves over is your step over. With those, there's only one flute on it. So when it moves over and it travels, it's going to have probably a ridge. If that matters to you, if it doesn't matter to you, it usually matters unless you're pre-clearing material and then coming back for the flutes or coming back with the multiple flutes. But with this one, you would have that ridge, which might impede depending on what your goals were. So, but O flutes tend to move much quicker through material and clear a ton of material so you can get the job done, which is 90% of the work that I am tasked to do is like getting things done like right now. So we can iterate through, break something, and then come back and fix it again. So the analog to that in plastic cutting, you have different challenges with plastics. One of them is the plastic fuses in the flutes, which it also tends to do with aluminum, but you have a high likelihood of it happening if you don't treat it the way that it's supposed to be treated. So I like to use straight flutes, which are really good at evacuating chips. And with plastics, it doesn't experience those loads that it does with aluminum. So they don't need any kind of helix up. You just take these giant chunks out of the material. Again, the surface finish is a little bit much left to be desired, but for at least a lot of the cuts that we do, it's not as important as actually getting something on there and figuring out if it's going to work or not. And then you can go back and run these things called finishing passes where you would clear it and then you come back either with a different end mill or you come back with the same end mill, go slower, or you take less of a depth of cut so you don't have all of those vibrations and issues that you'd run into. I don't think that I'm actually going to go into this video part, but that's going to talk about your upcut, downcut, and some visualizations, which may be helpful. And I'll go ahead and share this whenever I'm done. I'll probably edit it just a little bit more and then bring it on. So the next kind of thing to keep in mind is design for manufacturing. When I got this part from the group that expected me to cut, it was all curves. There was no parallel sides to it. So there was no hope of either clamping it into a vise or indicating off of it. So it was pretty miserable. We had a long talk about making sure that this can be kind of setting the manufacturer up for success. And because they wanted features on both sides, one side of this had a pocket, I think, cleared out. There was a couple countersunk holes. And then this other side had this pocket, and then it had a fillet to accommodate some piece that they have. So add all of those together and it makes for a pretty terrible day. It was done that way because they used this thing called topology optimization, which minimizes the amount of material you have, and it still generally maintains the integrity of the part just based on the loads that you apply to it. So it's a really cool way to go about things, but it can be pretty awful for the person who's making it. And if you're making this for yourself, you have to think about, how am I going to cut this? How am I going to set it up? How am I going to re-indicate on this part to cut the other side? Because if you cut one side and you flip it over, how do you ensure that you're going to cut in the right spot? So we created a fixture on the bottom where we cut this box out of the high density polyethylene with the straight flute. And then we came in and cut, no, this one had cuts in the corners. And that gave us a box. And the cam that we set up had the origin right here. So after we cut this box, the origin was still set in the exact same spot. We arranged everything in such a way that we could flip this over and bring it back. And then all of the origins for the whole piece and the bottom part were off of this one origin point, which made it really easy to cut this part right here. You'd be pretty much guessing, or you'd have to break out an edge finder and a bunch of other things that are not too common practice, at least on these hobby grade machines. So definitely keep that type of stuff in mind and think about, if I put features on both sides or I put some weirdness on it, am I actually going to be able to mount this thing and then make it? So that shows you kind of where the fillets are. So we did all of those parts, and then we came back, pocketed it, and then we used a ball nose, which has a curve at the edge at the bottom, and it grinded that straight part into a fillet, which is what they needed for their design. So this follows along the same vein as they also wanted another part that was a little bit smaller. It had countersunk holes on the backside, and it had a pocket, or it had a pocket here to clear that material because they had to fit this onto, I think, a brake caliper. And then they wanted to fill it too, because if you don't add the fillet, there's a thing called stress concentration that can lead to failure, premature failure. So they needed to have that transition curving downwards into the part. So we did the same thing with this, except if we had taken the same idea with the last one and said, okay, we're going to cut this part, we're going to put it down, we got our 0. Okay. Well, if we did that and we just cut with the end mill all the way around, even if it's small, use the smallest cutter you can find, it's still going to have a really small radius at the edge. So I saw this trick on one of the websites that I'm going to recommend called NYC CNC, and he cut the corners out of it as one of the operations, and then this lets this sit into this corner without having to worry about a radius, which turned out really well. So we did the same thing, cut this corner, did the holes, placed this, we still had the 0 here, did the front features, and then flipped it over and did the back features, which are these countersunk holes, which had to be exactly where they needed to be. So that was an adventure, and we're actually going to go back afterwards, after all of this, and I'm going to show you the cam that we made for it, so you can sort of see the process starting from a block to what we see here. So here's some more examples of CNC parts that we came up with and had to sort of get kind of creative with, because each one kind of proposed its own new issue. So with design for manufacturing, if you have a regular hobby grade CNC or whatever like this, and you need features in certain spots, and they're massively different sizes. So let's say that there was a 3.5 millimeter tap hole for this corner to mount something. And then the rest of it was a ton of material that you're clearing out. Like let's say the whole middle part of this was all cleared out, which underneath these buttons, it is cleared out. They put it all in there. So we're not gonna take the little itty bitty end mill from here and try to do all of the rest of this stuff because it would take absolutely forever. We used 2 or 3 tools for this one, which could end up posing their own problem. If you accidentally lose your zero, let's say that you set up your cam for this corner, you say, okay, this is where I'm gonna do everything from. I'm gonna run all this stuff. So you do your first one and you do the little holes and you do that 3.5 millimeter tap drill size, which is gonna take a very small bit, could be a drill, could be whatever. And then you wanna switch over to the bigger end mill. You have to re-zero for these particular machines because the length is different. So if you tried to just throw a new end mill in there, swap over to the next tool and run it, it would have no idea how tall that end mill was. And it would probably either drive it down into the workpiece or it would just never even cut. So the more operations you have, the more tools that you have, the more of an opportunity for bad things to happen. Unless you have a machine that has an automatic tool changer or ATC, and those can get pretty expensive. So keep all that in mind. If you do have access to a nicer machine with the ATC and you can run different tools for everyone and they're all preset in heights and it knows all that, it's beautiful. I've been on a few machines that has it and it's a whole different world in your workflow. But does that exist with you? Do you have those capabilities? If not, maybe try and make everything a 4 millimeter capable. Can we put 832s in here or 1032s instead of 3.5? Is there a reason why it's so small and so big difference? So think about that when you're moving forward. With this guy, this is a big piece of aluminum. It doesn't look like it, but it's something like 3 inches by 2.5 or 3 inches in this way. And then it was one giant block. And we had to clear all the material from the inside of this. With it being so big and with the end mill having to be so long, as it travels down into the material, it's cutting. If you're taking a heavy load on it and you have this huge tool stick out because you can't have it right here or it's going to run into the workpiece, if you have it up here, you have more of a possibility for it to kind of move around like this instead of moving through the material because of the deflection from the tip. And it also could have issues with it being spinning non-concentric with the axis of the spindle. So if there's a way that you can maybe minimize the amount of depth, could this be shortened? Could this have been done a different way? Could you make it in a couple pieces and then put it together in some way? Those are all things that you might want to keep in mind if the goal is to have it in a certain precision, a certain accuracy at the end of the day. And with this, it did have to be a certain size. So we ran a ton of finishing passes at the end, and we were real careful about how it was held on to the bed, which you may be able to see. They have extrusions on here that have places for you to put fasteners in, and you can hold it down with the fasteners in multiple different ways. And I don't think that I'm going to get too deep into fixturing. However, it is very, very, very important to make sure that your workpiece doesn't move, and specifically it doesn't vibrate if it can move a little bit, because you're losing a lot of the chip evacuation capabilities and it can lead to a pretty bad day. And I've seen workpieces just get completely ruined because it wasn't held down properly. So on the other side of that is you need to make sure that you know about the speeds and feeds. So the speed would be the spindle speed, how fast the end mill is rotating in RPMs. And then your feed rate is how fast it's moving through your material. And the combination of those two, people literally have doctorates on these things to figure out what is the best approach, what is the best speeds and feeds for this material, for this particular end mill. Like, everything is really, really important, because you can introduce issues if you don't have the right speeds and feeds. With the O flutes and some of the ones where it's a little bit more forgiving, if you're off a little bit, then it's not as big of a deal depending on what you're trying to get out of it. But there are proper ways to calculate the capabilities of the machine. And then if you can figure out what's happening and how much material you can move, called material removal rate, over a time span, you can compensate too. So if you say, okay, this is going to move like this as it moves down, maybe it's undersized 4 or 5 thou every single time you cut, you can give it an offset for 4 or 5 thou, and then you can make up for those problems. Usually. Sometimes it's a surprise and you're not sure exactly why it did the things that it did. So you have to look back through your cam, find out why you chose the tool pass. So there's a couple references on here. One of them is really good. It's called CNC Cookbook, and that's kind of the place to go for a lot of your going into the CNC world. They have, I think, forums. They have all sorts of stuff. So the next one is a YouTube channel that I love to watch. Is NYC CNC, and they deal with a company called Tormach, and those are fairly high-end machines, and they use Fusion 360, which I've grown to deal with because of the capabilities in their CAM process. And they have the Autodesk Fusion 360 has built-in manufacturing post-processing capabilities that makes it a standalone unit that's capable of doing a bunch of magical things, like adding, for instance, these things called tabs between your pieces so that everything doesn't vibrate off of your cuts, because you're taking full cuts all the way around. And you don't really get those, you don't get that capability from SolidWorks plugin from the same people called HSM Works because of whatever reason. And there's another thing called nesting, where you can take all of your parts and put them together in like the best little small package. And that's great for a bunch of different reasons, making sure that you can, all of your material doesn't get wasted. If you spread it out, you have these pieces in between, that's a waste. But if you can bring them real close together, that's great. Haas has some awesome things. And this was actually one of the things that I'm going to click on and kind of show you is the video that they have on speeds and feeds. And he goes into some of the math and the ideas behind where you get these numbers from, because they're not arbitrary. They can kind of be if you just do it, run it, it works. A lot of people run that way, but you're not lengthening the tool life, and you're also, you might be running operations that are wasting your time. You could do it in a more efficient manner. So it goes into a lot of details about SFMs, like surface feet per minute. Your RPM is your spindle speed. And then you can derive those numbers for the speeds and feeds based on your tool diameter and converting it over to what you need. So he's got a lot of really cool stuff on here, and then I'll add that to the PowerPoint so everybody can kind of see it. On the other side of that is being able to look at the websites from the manufacturers and finding out what they recommend, because although they're usually pretty, ambitious with the speeds and feeds that they recommend, if they do, it's still a really good starting point to maybe divide it in half or something like that. So this one is a company called Amana Tool, and they make really good stuff. Again, O-flute, like my favorite thing for aluminum, but you can go down to the speed and feed rate, and it'll give you your whatever diameter you're looking at. And at least I typically run 4 millimeters, and any of the cutting height, shank, all that stuff, that's not what I'm looking for. It's going to be down further, I think, at the bottom. No, yeah. Let's go to 4 millimeters, and let's make sure that this actually shows up. Probably should have had that. All right, well, so there we go. So there's a PDF that they have where it'll tell you what is your feed rate at 18,000 RPM based on what they predict from it. So I run a 4 millimeter. They say you can do 35 to 70 inches per minute, and surface feet per minute is not what we've talked about before, but you can go into more detail reading into the specifics, but you can derive a lot of your things off of the RPM and the surface feet per minute, and then the diameter of the tool. This thing is the chip load per tooth. I'm not going to really go into that too much either. I think that it's better if you watch the videos that are dedicated to it. But the combination of all of these guys, and then maybe dialing it back just a little bit, can really get you a good starting point for it, because it's the most efficient way to move through the material with their tool. And then they give you how to find RPM as that surface feet per minute times 3.82 divided by the diameter of the tool. And he goes into the details of why that 3.82 is there. So that's why I like the combination of those two. Harvey Tool is also a really, really good resource. A lot of people buy their stuff from them because they have numerous resources, and they have a good relationship with their customers, and they put out a really good product. It's a little bit more expensive, but sometimes you pay more and you get more. So they have the speeds and feeds that they recommend, the coding, which we'll talk about a little bit later, and then they have the CAM tool libraries. So the tool libraries are amazing. So you can download their tools for your machine. And for instance, if we did this guy and I wanted to change, the tool, but I needed to make sure that it aligned with something that I bought. Instead of having to go real deep into developing the geometry of all of the things that we would buy, maybe buy a lot of stuff from China, trying to define that is going to tell you a lot about the tool itself. So let's see if this actually populated or not. Roland, Shipoko. All right, so this is a facing end mill. I think this is one that I made, and it doesn't have the same geometry exactly as the facing end mill that I purchased. This, I believe, is the actual facing end mill that we have. And I did tell it the number of teeth was 3, or number of flutes, number of teeth. And then you define the diameter. This one is the 9/8, so that's not actually the same one, but this would define all of those. And when you go into it, if you save these guys, they're going to save the feeds and speeds that they recommend from the manufacturer and from yourself, so that you move forward. And that those offsets, you'll find maybe I can move 20% faster through my material than the manufacturer. Maybe I have to cut it in half. And if you update these, then you can continue using those tools into the future. So it's about setting up maybe the next people who end up using the same tools. And that's what I've been doing on these guys is figuring out, okay, if I know that I'm using an Amana 46229 or whatever, this wasn't mine, by the way, this is a download. It has the spindle speed, all of those things. The only thing that you would use, I could change it. The only thing that you would probably change from this is you could change how much it spirals down into it or how much the depth of cut is. And that makes everything fairly straightforward. So we have a bunch of different operations on this. I'll go a little bit deeper into it, but that was a really good resource. GWizard is by the same people, CNC Cookbook. That's a calculator where you can put in a lot of details about your machine you're using and it'll give you more of the speed rate. I think you can get around the right speed without that, but if you're really trying to minimize, you want to maximize your tool life or you want to really dial it in, it's a great resource that they use on an industrial level sometimes. And then Millwright CNC is this right here. I downloaded on my phone and you literally click like 1/8, 1 flute, you run conservative, click aluminum and then calculate and it tells you the feed rate and depth of cut. But that's based off of their machine. And then also sometimes it's either aggressive or it's too conservative. So you have to kind of play around with that, but it's a good starting point because that can always be the killer for your tools and you'll end up breaking tools because you're going too slow, too fast. It's really easy to get a lot of that stuff wrong. So with the cam packages, I generally like to recommend HSM Works because we use SolidWorks here and I find it a lot easier to run through the cam process with HSM Works compared to even the built-in cam because of how user-friendly everything is. And the Autodesk people did a really good job of porting it to Inventor and to SolidWorks to have the same tabs whenever you're doing your profiles. All of these tabs, as you click through them, are essentially the same thing that you'll see on Fusion 360. And it'll be the same thing that you see on Inventor. And it makes it real useful to switch from one to the other, in addition to the fact that it's very user-friendly compared to a lot of the other stuff on the market. So that's one of the things that I generally recommend is either running it through 360 if you can, import whatever your part is and then do it from there so that you can take advantage of the tabbing and the nesting capabilities, or at a minimum using HSM Works, which is free to students, SolidWorks, which I think is free to most students, or I don't know, at least at UF it is, in the mechanical department. Or if you want to do an Autodesk and you want to run Inventor, that's free to students, and then you can install the plugin. So it really kind of works out pretty well. And then for the design side of it, the normal things, there's a program called Vetric Aspire, and then there's lesser ones that do things, but they're really good for being super straightforward on really simple 2D cuts. If you're just doing a bunch of gussets or you're doing a bunch of belly pans or stuff like that, it minimizes the extra stuff that you'd get from Fusion 360 and like the 3D tool paths. And you wouldn't get with this you might, but the lower end ones you wouldn't get the ability to do the contours that you need in 3D space. And then you can take the stuff off of Onshape and then you can import it into one of these other programs, but I've never done any cam straight from Onshape. If you can do that, maybe you can. Reaching into the operations that we generally run for, let's say, this piece right here. Whenever we cut it, the first thing that we did is set everything up and made sure it was oriented in the right place. And we were cutting off of either the top or the bottom. And then we didn't need to do a facing pass like we did with the other one, but doing a bore and clearing out this material and doing a 2D contour and going around the outside is all we needed. So it made it real easy to go through those two. And I'll move into the other operations just to kind of give you an idea of what's happening behind the scenes of those pieces that I showed you in real life. But you have all these capabilities to the point where you can actually thread. This is a tap drill, which is pretty fantastic. And I think I have one. So instead of hand tapping everything, you can use something called a thread mill. And this thread mill would go down into your piece and it would cut those helixes, which your screw would tighten down into. And it's really convenient because you don't have to hand tap all of your things. It's a little bit more finicky than just running some of these cuts where it's clearing the material. You actually have to be really careful with what you do, but once it's dialed in, you can continue using those operations over and over again, which is another thing that I wanted to bring up. If you go to here and you create from template, you can create some sort of boring operation or something that you do all the time to minimize your workflow. I have all of these saved. So if I wanted to do a 2D contour with the 1/8 inch end mill out of aluminum, everything's set up already. I just have to select some of the geometry from my piece so that I can achieve those operations. So this has all of the feeds and speeds, and it also has the 1/8 inch end mill that I usually run. And if I wanted to, for instance, take out this right here, clear all that out, then I do that, make sure that this is one of the more important things, is making sure this arrow is on the side that you're going to take the material out of. So if you did it on the other side, it's going to be like a radius bigger than what you would expect. So if we did this and we just grabbed the top part and the bottom part, I know I'm going kind of fast, but I'm not going to go into that stuff right now. I might in a little bit. I made sure that the depth is what I needed to do, and that's already kind of set from that stuff that we were talking about earlier. And then it maintains all of these other parts too. So if I just click this, it automatically makes this toolpath that I've done before and I'm going to do again, except I never had to set up any of that stuff with the tools. It was all right there. So if you know that you're doing an operation over and over and over again, it almost makes perfect sense to just go ahead and make a template out of it. Or let's say we want to store a new template. Let's say, oh, well, like I'm always doing this right here. We make store as a template, you name it, and it's going to retain the tool. It's going to retain the speeds and feeds, and it's going to maintain all of the settings that you choose for that particular one. So you can kind of have your world. There's other things that you can get into, and if you hover over any of these in HSM Works, it'll give you maybe even an animation sometimes, but for the most part, it gives you a nice kind of synopsis of what it is. Oh, maybe that was on Fusion 360. All right, I lied. It's going to be these guys when you do go into some of the other stuff and you mouse over, it gives you a couple more details. So I know if I go here and then I mouse over the stock top and I say, okay, please don't make me a liar. Oh my goodness, it is making me a liar. Okay, here we go. So it tells you more about it. Retract height offset is applied and relative to retract height. So you'll get these tool tips. It's a lot kind of better in Fusion 360 that'll tell you, maybe it'll have like a picture of what you're doing or whatever. And it kind of like, I don't know, makes it. So here we go. Don't be afraid to do anything like this and say, okay, what is this actually happening? Or even look it up to see if maybe I don't fully understand exactly what it's doing. So that gives you kind of a good idea of a basic rundown of setting that up. And then it's going back to what method are we looking at? Are you looking at running a huge CNC? Are you doing it by hand? Are you running it in a 3D printer, manual? Are you using wire EDM? Do you have the capabilities for CNC plasma? Are you designing for somebody that has a CNC plasma setup, but maybe it's, you outsource it to somebody else? Well, you can take those capabilities and just implement them, but don't try to do anything 3D if you're going to send it to an abrasive water jet, because that's a 2D operation. And if you're interested in learning more about that, I'd highly suggest that you look up water jet, EDM, wire EDM, and CNC plasma. Most importantly, wire EDM. That's pretty amazing. So I think the final one was to make sure that you understand which machine you're sending it to. If it is your own machine or if it's for somebody else, it's typically not recommended to kind of share your G code or NC code, because anything can happen. But the post processor that you use is important in whatever machine you're going to use. So let's say I wanted to run this, and this is going to turn all of these paths into code. And I can actually show you what it looks like when you do it. And I'll say, okay, I'm going to do it in Mach 3 mill. This particular machine uses Mach 3 as the interpreter for its control stuff. So there's a ton of other ones. The Roland is what they have over in the other building. And then my machine, I wish it was a Haas, is GRBL. And that's all kind of like syntax differences between the two, just different controllers. But if you tried to send this Mach 3 to a Haas, it wouldn't work. It's like, what are you doing? This, I can't even recognize this file type, whatever, this is .tap. So if you post-process all of that stuff and you open it up, it'll show you the G code that it sends. And your machine is going to listen to every single one of these and say, okay, this is my first operation. The spindle speed is 18,000. And all of these operations, which I'm not going to lie, there's a lot of stuff that I have no idea what it's telling it to do. But I trust the machine for the most part. So it'll make sure that you get a pretty flawless execution as long as you're set up and the machine set up for what you send out. And this one's really, really long, but it goes one line at a time. So this is where it switches off, goes to a pocketing operation, changes the spindle speed to 17,000 RPM, and then it expects a different tool, I think. So you can kind of look through that stuff. There is on CNC Cookbook, they go into the G code and tell you what each one of these things mean down to the very specific one. So maybe look that up if you're interested. I've only had a few instances where I had to look up why a machine was either or something else. So let me cancel that. So let me switch back over. That's actually the end of that PowerPoint. I wanted to sort of emphasize the types of tools, which I went over, the safety of the machine, which I believe I went over, the way to kind of set everything up, the fixture methods I'll talk about probably real quick, and then I'm going to probably maybe take some questions if anybody had any. But let me talk about the fixture method real quick, because I think that it's pretty important. So I told you that if you have excess vibration, what it's doing is just basically, instead of it just moving through the piece, it's like shaking the piece, or it's pulling up and like hitting into it or whatever, and that's not being efficient. You can have a lot of heat buildup. You can have your end mill break if it gets too bad, or you can dole it out really well. So, or you can pick up because this is an upcut, you can actually, it pulls up on the material, and if it pulls up to the point where it dissociates itself from the machine, then it has the potential to launch those pieces into your general vicinity at very high speed. So this is one thing to really kind of pay attention to. And I like to use high density polyethylene as my baseboard, my spoil board, and we'll bolt these guys down and put something on top, and then drive everything down into it. And you can kind of see some of these indentations and cuts and everything, and that's what it's made for. So you cut these, this sits further down into it, so you can plane this with your end mill. You can go through and clear off that top part, just maybe 0.5 millimeter in total, and you now have a flat surface to work with. Fortunately, the HDPE doesn't absorb moisture the same way that MDF does, which is medium density fiberboard. That's a common spoil board that people use. If you run a bunch of your codes over the course of several days, maybe you're using coolant, it can soak into there, swell up, and now you have a Z height difference that you weren't expecting. So you might dig further down into the piece, it might not get to it, like there could be anything that happens. So I choose to use something that doesn't interact with the liquids, or make sure that I can repeatedly run the same operations and then cut the top part off and do it again. So this is a little bit thick. I make sure that I can run a bunch of 0.5 millimeter increments down until it's basically a throwaway time, and you would either practice on it a little bit and then replace it with something else, or you can go with the sturdier fixture method. So this one's actually bolted directly to the bed, and that's going to give you a lot less vibration. You unfortunately run the risk of maybe running down into the bed if you go too far, because the machine will do what you tell it to do. And if you tell it to just continue going down, it's going to continue going down until it can't go down anymore. So that's the kind of the benefit and the curse of it following everything you need or want. So I ran a couple passes on this guy so that I can fixture things down into it. And then my next operation is going to be a thread milling operation, so I can bolt things down. But making sure that your workpiece is secure, making sure that you're using the right end mill, making sure that it's actually designed in such a way that the tool can get to it, which you can run as a final thing. You can run a simulation of your tool paths to verify, not only you can look and see, okay, that's what it's supposed to be doing, but it's actually pretty cool to see it kind of come out of the stock. So you don't even need a CNC to practice CNC stuff. And that's what I'd kind of suggest everybody does if they can, because there's a lot of things that you can learn from this process. So if you make something, cam it, and then run it, let's turn this down just a little bit. You can watch the path as it's going through, and it'll show you either maybe the tool's too short. It'll throw errors down here saying, oh, I ran into the workpiece, or it'll it'll show you that, okay, I can't get into this one spot. So that's kind of the huge benefit of running this type of cam, is being able to predict pretty well if you're going to run into any issues. I like to, after I'm done with all of my stuff, I like to start with kind of a block like this and run through each one of the tool paths and see if the machine is telling itself to do anything kind of crazy. It might drill here and then go over here and like do some weirdness and go back over here. I'll say, oh, maybe I accidentally selected this little edge and I wasn't supposed to, and it thinks that it's part of the cut. So it gives you a good idea. So I think that addresses maybe some of the concerns moving forward. I can talk more about the choices we made with this, but I think that it's pretty fair to kind of ask questions if possible. So let me see if y'all had any questions.
Wait, so if you didn't have access to like one of these machines, how much would it cost to like send it out and like get it made?
There is a service online where you can find out how much it's going to cost. It really depends on how you design it. So a lot of the stuff that we talked about is like designing for you and making sure that it's a small like M2.5 and you're switching to this other thing. Is it going to have to be like a rotary axis where they have to use a different machine? Are they going to have to use special tools if you're going to use exotic materials or something like that? So there's kind of like that caveat as like, it depends, but you can, I'll actually, I think, post the website where if you put in your part, they'll go through automatically kind of and figure out how much it's going to be. There's a whole service, at least online or whatever, there's a whole situation where you can get quotes and find out kind of who does the best and what you do. And then you can find out how much it is and then run it off to there. But to give you a blanket, oh, it's going to be $250 for you to do this, that's just not a thing.
Dan, since you're in mill, do you know like other people in mill that also do CNC?
So Jackson, and he's leaving. Jackson's brother is not leaving, and I think Jackson's brother is the person that actually owns this. They used it the most. So they have some capabilities. I don't know to what extent. I haven't really talked to either one of them to at length, but it's my understanding that there isn't a lot of knowledge in here of any of this.
Jackson's younger brother's in my grade, so I was just asking.
Yeah, so he did. I think this was bought for FTC. It just happened to be easier for it to be here, I think, and then cutting and all that stuff, and it worked out in other people's. So they used it before, and then they did some cuts for swamp bots. Yeah. So they have some capabilities. I don't know to what extent, but that was something that I talked to Dr. Schwartz about, and he said that it'd probably be a good idea to reach out to other people to see if they were interested in kind of like taking the ball and running with it.
Okay.
Yeah.
I was just asking because Andres texted me about doing manufacturing in mill.
Right.
Also, since you told him.
Yeah. And he doesn't really, I don't think, let's see, Juan didn't. He knows kind of the math behind it, and he's done a little bit of the hand machining and stuff, but I don't think that he's done anything extensively with this. So it's kind of between those two people and anybody else that you find in that had hung around DML or something like that, maybe. I don't know. Or if you just get addicted and start cutting stuff every day like I do.
Yeah, do they just let you cut things in the lab?
I mean, I cut for, I'm working with them to develop these things. So I actually made a video, which I can share with all of y'all, about this particular machine and starting from nothing to something in CAM, but it's lengthy. So I'm going to try to narrow that down a little bit, but to me, it's interesting, but it can also be pretty long-winded. And I go through every like things to look out for or whatever. So if you're interested in seeing more details on that, then I'd certainly recommend that.
Okay.
Yeah. So this particular machine uses a spindle as opposed to the hand router like mine. So you have real-time spindle speed control, which is really important in switching from your different operations, because you can go back through with what they call I forgot what kind of pass it is. It's a finishing pass where they either bump the spindle speed up or they travel through it really fast because it's only 4 or 5 thou at a time, as opposed to, let's say, 20, 30 thou. So you just blaze through it and it gets that last little bit out of it. And that's what we did with the with this guy. Is we chose to do the caliper holes is like 4 millimeters. And then later on, let me see, went back with the 4 millimeter, I think, and then cleared out the inside Orioles right next to it. So it was kind of like those finishing passes. And that's, you can minimize the amount of actions that you need through there with like built-in functions. They have like finishing passes that you can run inside of Fusion 360 and all that stuff, SolidWorks, but it usually takes a long time. And 99% of the stuff that I run is usually pretty time sensitive as opposed to exactly on the money, precise and whatever. So yeah, but this machine runs that, and it also has air blast, which is great for chip evacuation. It'll cool off the chips, make sure that they're not as hot, so you can take more of a bite instead of it fusing into the flutes. And then it also has a air nozzle up top that it runs to isopropyl alcohol, and isopropyl is really good for aluminum coolant, so that you can take larger and larger bites out of it. If you can make it cool, and you can just start carving away at it. But if it gets too hot, then you run into those situations I talked about before. So it's quite a capable machine. Sounded like Ian was going to ask a question, or no?
I do not have a question.
Okay.
I have one, but
yeah, what's up?
is aluminum the like best kind of metal to CNC?
Again, I guess it depends. It's really, for us, it was the most versatile in both welding capabilities, if possible, in machining capabilities, so it doesn't get, depending on the alloy, it doesn't get really gummy or anything like that, so it's easy to clear it. It's pretty fairly accepted to have it pretty much everywhere, so you can get it at so many different places, so it's easy to acquire. And then the price is mostly right. And it's not that it's the best or even the best material for what most people use it for, because wood in many scenarios is completely acceptable interchange for the pieces that they use for like belly pans and stuff. People are like, oh, I'll run aluminum with webbing or whatever, all that stuff. And there's a ton of teams that run wood belly pans out of, I forget what the particular wood is, but it's a lot cheaper, cuts a lot faster, and it does the same thing. So, and sometimes it's kind of like a flex. The other times it's just easy to acquire, and the length of time that you can use it is typically better. So, but you can run, when you start looking into your other materials like steel, you have to take other precautions, or if you're designing for those other machines that I was talking about, like you can do abrasive water jet, and that'll blast through steel And if you get a sheet metal sponsor or something like that that can bend things for you, or if you get a brake and you can bend it in your own way, then that's certainly a super viable option. I think 1902 does a lot of they definitely do a lot of bending, and I think they use steel, but they have a sponsor who does a lot of their bends. So it tends to minimize the other stuff that we usually kind of take for granted. You could just drill through something real quick, or like cut out this hole real quick. So long answer to short question.
I have a question.
What's up?
What are the different types of metals you CNC?
I did copper yesterday. I've done aluminum. I've done steel. I've done all sorts of alloys of aluminum. So you have like, each one of the alloys might be better for a certain scenario. Usually the ones that we run is an alloy called 6061, and it has a really nice balance between durability, what's it called? Durability, strength, machinability, and corrosion resistance, which that's not normally a big deal, at least inside, but it's a nice balance between all of those things. But you can get another alloy called like 5052 or a 7071, and both of those have properties that set themselves apart in a certain way. Either they're stronger or they're easier to weld or whatever. But the steel is the hardest that I've done, and I don't know if this machine in particular was necessarily made for it, but I took very light depths of cut, and I was able to clear out enough material for us to finish the project that we needed. So that worked out pretty well. But I can't think of any other metals that I've cut. But with each one of those, I guess when you're saying design for manufacturing, if you choose a certain material for whatever reason, there's always a trade-off that comes with it. Like for copper, I did a cut for the Solar Gators, which is a team that they have here where they make electric / human, it's not human powered, but they basically just go as far as they can with solar power. They have a bunch of battery banks and stuff like that. And they needed pieces of copper, which are great conductors. Cutting into copper can be miserable because it's both, it can be gummy, and it also does something called work hardening, where if you move it too much, like quickly, then it strengthens itself, and then you can just snap your end mill. So you have to find a nice balance between the two. But those are the ones that I've cut. And then I've cut a ton of plastics. But I would stick with aluminum if possible, because of all the reasons that I mentioned. But it's not necessarily the best. So definitely keep your mind open to different materials. Cool. All right, well, I'm gonna post this somewhere. And then after I maybe add a couple more links in there so that you can see some of the resources that I recommend. The best thing that you could probably do moving forward is making sure that if you're coming up with a piece like this, I mean, why not cam it? I can walk you through the process, setting you up with like templates or something, so you can kind of see where each one of the different operations go. And you know that, for instance, if I'm holding this down with tape and glue, which is one of the methods I like to use a lot, where you literally put tape, glue, and then another tape on there and you put it down, it holds really well. But if you run your passes, if you end up accidentally cutting out in the middle of where you're doing your work holding, the last thing that you're going to cut, it's going to launch that piece. So keeping a lot of that stuff in mind is important because of the manufacturability and your work holding, all that stuff. So you might have to get creative sometimes to avoid damage. But I would say we could do a quick like show you a setup, and then you could kind of try on your own time to do a cam, and then we can work together to see if maybe we can make that happen in the future. Because I think the more you understand about the process, the better you can prepare for the actual cut, because the cut itself is 5-10% of the whole process. It's usually very straightforward compared to making sure that you do everything in the right order. You use the right speeds and feeds, you set it up for the right machine, you did all of these things, and then you put it on there, and it's like, can be a pain sometimes, but for the most part, a lot of the heavy lifting is on the front end. And that's where they almost feel it's like special when people do cam process, and it's like this black magic that nobody typically does. And it's really not that terrible. And you get awesome results out of it. So that's kind of what sunk me into it. But I can probably, if I did this, and we can talk about maybe some of the tool paths that happen on here. And we started by creating a piece, and that was their stuff. And we told it where the origin was going to go. And I don't know if you remember me saying, like, to make sure that this origin right here is going to define everything about where you put it onto the machine. So the machine itself is the X travels left to right. The Z is up and down, like into the ceiling. And then the other one is into the wall. So it's like Y, X, and then Z. And if you, for some reason, take this and you put it, let's say, over here, and it's facing, the X is facing this way and the Y is facing this way. If you tried to put this on the machine, you did your 0, it's going to try to cut this way. So it's really important to make sure that your coordinate system aligns with the coordinate system from whatever machine you're using. And some machines are weird. Some machines, the positive Z is downwards, and other ones, the positive Z is upwards, which can make it real odd. And then you define where that goes. And there's a lot more to it, but that's going to set your workpiece up for success. And if you were to look at some of the paths that we chose, this was a pocket with a 4mm, and it just went down, cut into it. And we continued to go into different pieces until we got to the very end, which was the outer contour. And at that point, we've done all our critical features on here. And then now we're doing the outside, and then we're ready to, I don't know why we did that contour first. Maybe I suppressed those and then went to it. Yeah, so this was the pocket that cleared the rest of this stuff. And then the finishing pass just took off like 4 thou. And then I left a little bit. Oh, I know what I did. I left a little bit on the bottom so that I could come back and clear it. And that's what this last one did. And then I don't know why that's there. But then we flipped it over, and now, so I'll show you this guy. And then when we flipped it over, now you had to make sure that it aligned with the machine again. And that's what we did. We put the X this way, the Y this way, and the Z this way. And we're going to be cutting these guys based off of that one part that we kind of identified as our origin. So it goes definitely deeper into that, but that kind of gives you an idea of at least the setup. And then you can go through some of these guys. And if I didn't create a template already for it, then you would have to choose the tool from your library. The coolant doesn't really matter on this particular machine. Some of them, you can tell it what you need to do. And then you do all of these guys and travel through these tabs. And that's one of my favorite things about the Autodesk environment is for each one of the tabs is sort of like, okay, the first one is speeds and feeds. What tool is it? How fast are we going to move? The next one is, okay, what am I actually cutting? Is it this right here? Is it, turns out to be this right here, but what area of interest do I have? And then it has some extra material. So this guy on the next one, all right, I'm cutting from where to where? Am I starting above the top part for some reason? Am I starting further down? Is this material already clear to the point where why would I do all my tool paths coming from the top if all that material is gone? So I can select here, I can select here, and then we went down to here, because if we went down to here and we did that, it would go, this would go all the way through that material. So you have to give it its limits basically. So that's where kind of that comes in. And then you go through and do the same thing with kind of everything else. Is we go from there. The next one is, okay, how many should I do multiple depths? Am I going to do one solid cut through it like I do with wood, or am I going to do it at 25 thou at a time? So this will tell you, okay, this is how far I can move axially as the depth of cut or DOC. And then the final pass or the finishing pass is going to be like 8 thou. Do I want to do even? There's a bunch of options that you can have. This is important because this is how much, whenever it goes over, how much does it clear as it steps over into your material. You can get pretty aggressive with your depth of cut, and then the radial depth of cut or the step over, they use those interchangeably. I would have to bring that down to compensate for that, because you can only take away but so much material at a time, depending on what material is. Okay, so the next one is, okay, I'm going to helix, which is, it actually gives you, I think, it doesn't give you. Man. All right, it doesn't give you, but helix is whenever it just goes down like this, and you never want to plunge with this CNC unless it's made for it. You typically want to use a drill bit to drill down into it, and then you would come back in and clear the rest of the material. So if you're moving into it, you want to do one of those guys. Helix just does some pitch down into it. You can do some kind of profile, or you can just plunge down into it, depending on what it is. But I recommend, at least with aluminum, to definitely not plunge. Even if your cutter's made for it, I would at least try to pre-drill and then go through that hole and move into it, because that's really hard on the end mill. So that's, I guess, a pretty broad overview of that. And I think that is a pretty safe time to ask if there was any more questions, and then kind of wrap it up for now. Are y'all feel all right? I know it's a lot. Yeah. All right. If y'all have any more questions, ever, send me a message. I can talk to you about it. The more that you see and the more you kind of work through some of these guys, you learn your capabilities and you say, okay, maybe I shouldn't have done that this time, or maybe I could have done it better, that type of stuff. And that's how I learned. Is I broke a lot of end mills, lots of tears, but made it through, and it ended up giving us a lot of capabilities and doing some pretty weird designs compared to just doing like caught stuff and then paying $1 zillion for it. So go forth and be merry. I don't know. So I'll submit the other videos so that anybody, if they wanted to see this particular machine or mine, you can find out what the actual like physical setup is, and it'll go into a little bit of detail about the fixture method, which is also incredibly important, but it's nothing that I can kind of go into now. Well, thank you all for your time. I'm going to stop the recording.